All right, so we're talking through interactive or numerical control variables. So we've spent, the progression we've gone through this semester is really just introducing the core tool set. Like I mentioned, there are lots of fancy things you can do with data, but what we do in the field, almost every area of science uses one of the core skills we've developed. At least like 90% of the models we run are something that we've talked about in this class. With some nuance, there are more complicated extensions of the things we've done. So not every model you'll see looks exactly like this, but the core ideas are something we've covered. At least 90 to 95% of the models you'll see look something like this. The last thing, or one of the last things we need to do is talk about control variables. Last class we talked about combining interaction terms with multiple intercept models. So we have multiple slopes and multiple intercepts, which gave us a lot of flexibility in the models we could build when we're testing relationships or average effects like we do. But I want to show you another example. This is something that we couldn't do using the model we built last time. And this is the last sort of core piece before we start turning our attention to the final projects. If I were to, so I have a data set on Pittsburgh housing prices. I have lots of information on each of these parcels. And my question for today is, what's the value of 1 additional square foot of living area? So, using property values, I want to try to test how much people are willing to pay for 1 extra square foot. And we're going to get a number. This is property values coming directly from the city. And the problem we're going to run into is that housing prices depend on a lot of things. So first off, we have square foot, age of the house, number of bedrooms, where the house is. So, like, if you live in Oakland or Shadyside or Squirrel Hill, Highland Park, these are areas with expensive houses simply because of their location. And in a lot of ways, a big part of the value of a house is what you can get to directly around it. But these are just a few of the things that impact the value of the house. There are really just a huge list of these things, and generally we don't have data on all of the factors that contribute to house prices. I've had a lot of students actually work on housing price models in this class. So if that's something you're interested in, this is a great data set for that. It comes directly from the city. So what I have here is housing price data with over 10,000 homes. I think the data set we're working with is actually more than this. But it's something of this size. We have a couple of key variables. So I have sales price, which is the price the house sold for the last time it's sold. So this is not like an assessed value. It's not like a zestimate, like the estimate from Zillow. This is how much it's sold for when it's sold. We're going to construct a log price. So sales price is definitely something we should be logging. The price of there are very few very extreme house prices, and there are many prices that are not that extreme. So this is one of those classic examples of requiring a log. Really anything with a price on it, I would say, requires a log. It's not a general rule, but it's pretty good. And then we have finished living area. So this is the square footage that's finished. And if you don't know this term, finished just means that it's nice. It's not your basement where the floor is dirt. It's something that's been the walls are nice. There's normal house things in it. And then we have the year that it was built. So this will tell us, how old the house is. So we're going to use these variables. There's many, many more in the data set. So like number of bathrooms, the number of bedrooms, these kinds of things. There's even information about location, so you could control for, you could include different intercepts for different neighborhoods. These are all things you can do. So what we're going to do is set up two different models. I have two questions here. The first one is whether housing price is related to the living area and whether it's related to the year it was built. So are bigger houses more expensive and are newer houses more expensive? And all I'm doing here is just plotting a scatter plot and then drawing like the basic regression line through the data. You can see vertical axis is log price. So this will be natural log. So every time, it's sort of in like scale terms. Every 1 unit increase multiplies price by the exponent E, Euler's number. And then the horizontal axis is finished living area. So this is, bigger houses are further out. So here you can see, generally the larger the house, the more expensive it is. Although you can notice a couple of other things. There's more variability in the price for small houses. So some small houses are very expensive, which is, these are probably downtown or in Shadyside or Squirrel Hill or Oakland. Any questions here? What?
What is the base price? It's like e to the 15 is like per million.
E to the 15?
Yeah.
3. If e to the 15 is 3 million, these are selling for 3 million.
Okay.
Uh,
I didn't
yeah.
know it was like thousands of dollars or what.
Yeah, so it's the natural logs. That would be right. So if you're saying e to the 15, I can't do that math in my head. But yeah, this would be a couple million. But it drops off really quickly, right? Because it's exponential. So we would drop by, e to the 14 is 15 million divided by e, and so on. Yeah, any other questions here? So this is interesting. This is, I think, generally what I would expect. Positive relationship between price and finished living area. And then the other thing we could do is plot on the horizontal axis year built. This kind of looks like a time series. This is not a time series. The horizontal axis is time, but we're not connecting observations through time. All we're doing is plotting the year that it was built against the log price. You can see some old properties are pretty expensive. So this is why it's 15. What did you say? 3 million. Yeah. So this is roughly $3 million, which is a house that was built in the 1800s. So I don't know. Maybe that's like I don't know if you call houses antique, but yeah, some pretty expensive houses up here. And then we have a lot of very small values. We'd have to look at exactly what that is. It says maybe e to the. This is some rounding number. So this is very, very small. Okay, any questions here? Newer houses are more expensive. Also, larger houses are more expensive. These are things you would expect. There's a lot of detail here. But one question I might have just looking at this is, I mean, when I'm looking at newer houses that are built, like the newer the house, the larger it is in general. Like old houses are smaller and newer houses are larger. So I have these two positive relationships between log price, finished living area, and year built. But I'm also realizing that these two variables are related to each other. So what I'm going to do next is just plot these two things together. Horizontal axis, I have finished living area, and then vertical axis, I have the year built. You could flip this if you like, and maybe in your notebook you'll do that. But when I look at this, I see maybe a weak positive trend here. It might be that they're, not that positively related. The correlation I put on the slide here is like 0.15 to 0.16. So there's a bit of a relationship. Newer houses tend to be maybe a little bit bigger. But my question is, if newer houses are larger, but we also see that larger houses are more expensive, is the expensiveness of newer houses due to the size? Is the reason that newer houses are more expensive simply because they're bigger? Or is there something else going on? Is it that newer houses are just nicer in their own way? And neither of these figures allows us to do that. So what we're going to do is build a statistical model that allows us to compare two houses built in the same year and check and figure out the extra value of houses that are larger compared to two houses built in the same year. That's going to be my main question. So how do we do that? Larger homes are more valuable simply because they're newer, which might be a conclusion we could draw. So this is, you tell me if you like this picture. This is the way I think about the model we're about to build. In 2 dimensions, we have a scatter plot. But we can also think of data in any dimension we like. Here what I'm doing is plotting in 3 dimensions all 3 of our variables. So vertical axis, I have log price. Horizontal, one of the horizontal axes, I have living area. And then the other axis, I have year built. One of the figures we drew before showed just the data looking at the 2 axes, year built and log price. So maybe you'll really dislike this figure, but if I look at the data sort of like this, so I'm looking at the model that I'm building just from this angle. This is going to look a lot like the model we built predicting log price with year built. We're sort of looking at the data in one direction, ignoring the living area. And what you can see is we're going to try to estimate a model that gets as close as it can in this one direction. So we're sort of looking at the surface I'm about to draw just from this one direction. The other thing we could do is plot simply in the living area direction. So we have this nice surface, which I'll come back to in a second. But on the vertical axis, I'm going to have log price. And then on the horizontal axis, I'm going to have living area. And I mean, this one looks a little bit funny, I guess. But what we're doing is, what we did before with the 2-dimensional scatter plot is basically look at this data and this model from this direction. We're saying, we're trying to see just the relationship between living area on the horizontal axis and log price on the vertical axis. And that gave us just a line. But what we're about to do is go from lines in 2 dimensions to planes in 3 dimensions. these kinds of models. Okay, these are really hard to visualize for, I think, obvious reasons. We have 3 dimensions. Anything in 3 dimensions is just more challenging to visualize. But this is the kind of model we're about to build. We built one in this direction in 2 dimensions. We built one in this direction in 2 dimensions. But what we're about to do is build a model in 3 dimensions. And what this model is going to let us do is compare 2 houses built in the same year, but with different sizes, and then compare their prices. Okay. Do you like this figure, or do you hate it? I see 1 thumbs up and 1 head shaking no. I understand. Oh my goodness, what's going on with my... Sorry, y'all, having technical issues. Okay, I'm not sure what's going on with OBS. I'll check back in later. Sorry for the interruption. I used to be a technical whiz. For some reason OBS is just giving me problems. Okay, so that was the model, the visualization I use often when I think about this. If you don't like thinking about 3 dimensions, that's really A-okay. There's no particular reason to need it for implementing the models we'll build. But if you like the 3-dimensional intuition, that's available for you. So what we're going to do is essentially extend the idea of a best fitting line into multiple dimensions. So we talked about minimizing mean squared error, so how far the data is from our model. I think it's pretty intuitive to do this in 2 dimensions. The analogy extends into any dimension you like, but we're not going to visualize it. So the model we built with our single variable, or one of the 2 we built, was this one. So we're trying to predict log price using living area as a predictor variable. And what we're about to do is build a model with multiple variables. So we're going to look at log price. We're going to predict it with an intercept term, and then we'll predict it with the living area, just like we do in the single variable model. But in addition, we're going to include year built. This is, in a lot of ways, very similar to the kinds of things we did last class, where we included a binary categorical variable as a control variable, as a predictor. But here, year built is not binary. This is any given year. So this tells us, this allows us to control for many different levels. And it's more than 2, so it's lots of different categories. And the way we would interpret this, our model 2 with multiple variables, is that beta 0 is the base log price. So this is when living area is 0. So as a house of 0 size seems reasonable, right? This is that's the price of my tent. And then we have year built. So this is using some base year. So I'll show you what this uses later. But that's the interpretation for beta 0. So it's the 0 in all of our categories. Then we have beta 1, which is that's the variable, the coefficient on living area. So the way we interpreted this before in the single variable model was this was the effect of 1 more square foot. So this was essentially just what happens to price when I move my square foot up by 1. But that's not how we interpret the multiple regression equation. What we're doing with the multiple regression equation is also saying that we're comparing 2 houses that were built in the same year. So we're going to compare the two, yeah, I said that already, 2 houses built in the same year. And then the third variable here is beta 2. So this is the same idea as beta 1, but just applied to living area. I'm sorry, to year built. So this is the effect of being built 1 year later while holding the area constant. So we're saying what happens when you increase the year, but the house size stays the same. So a house built in 1973 versus a house built in 1974, but with identical sizes. How much is that later house worth extra? So that's beta 2. And so everything is very similar to what we did in our earlier models, except here we're just adding this ability to hold the other variables constant. Okay, so going back to our original question here, what's the value of an additional square foot? Well, we can estimate that under some assumptions, right? Like what we're going to do is control for some of the things that we observe. These are all built on the assumptions that we bake into our models. So without controlling for a base year, a model would give us an increase in value for additional square feet coming from a couple of sources. One would be comparing old and newer houses. So we know that newer houses are bigger. So when we look at the extra value associated with a larger house, it could come simply because of the larger house being built in a newer year. So we're baking in some other related variable into our estimate. The size is the effect of increase in age impacts our size estimate. That's the core idea, which in this case I would expect would overestimate the value of an additional square foot. So what we're going to do is control. So we're just going to add that control variable. And what it does, this is maybe funny wording, but what it's doing is comparing houses of similar age but have different sizes. And then we just get the estimate in that way. So we're sort of in 3 dimensions kind of slicing in the size dimension. Okay. I wouldn't necessarily, I think this is kind of funny wording here. Who wrote my slides? Thank you. That one always gets a laugh. I don't know why. I guess it's funny. I'm not sure. I wrote my slides. So that's the idea. This is what we call a control variable. We use them very often. In fact, I think most models you'll see have some control variables. We'll talk next class about how we pick them. But this is one of the big ideas. So here are the 2 models. I ran them separately. The first one is just living area. So I'm using an intercept term and finished living area to predict log price. So what you can see is the intercept is log base 10, and then we have finished living area of 0.0005. So, the value of an additional square foot, a square foot is like this big. So what's the increase in the value of your house for an increase of this size? It's pretty small. You could use different units if you like. They're all going to give you the same estimate. just with different numbers. And then the second model, I'm running with a control variable. So here I'm running finished living area, but with year built as a control variable. And you'll notice a couple of things here. First off, the estimate for the intercept definitely changes. So the intercept is now negative. We'll come back to this in a second, why this went negative. But the second thing to notice is that the estimate for living area is, at least with this approximation, with these units, is identical, at least rounded to 4 decimal places. So these two are identical. Which, when I look at this, I think two things. One, maybe we need to include the 5th decimal place just to see if there's any differences. But two, I mean, I'm not seeing a big difference in the estimate after including this control variable, which tells me that the age effect is not a strong predictor. The relationship between living area and year built is not strong enough to see a noticeable difference in the estimate for square foot on price. Okay, any questions here? So these are just two pictures. What I've done, so horizontal axis, I have finished living area. Vertical axis, I have log price. And here what I've done is actually extend the rounding. So we're not rounding to 4 decimal places now. And this first one, I have finished living area with the data without controlling for year built. But then for this second one, I've actually, I've run the model, and then I've controlled for year built, and then plotted what it would be without the year built. So there's, it's like a partial residual plot. So I'm just sort of pulling out the part of the price that comes from age. And then I've plotted the rest. And what you can see here, if this is sort of the unrounded version, this rounds to the number we saw in the previous slide. And what you can see is the slope is slightly less. Some might even say this is a meaningful difference between these two. This is something you could test, whether adding the control variable meaningfully impacts the estimate for the impact of finished living area. And we'll talk about this next class, like how do we know whether we should include the control variable. But this is interesting. So this is the slightly flatter relationship between price and finished living area. So including the control does something, even if it's somewhat small. And the way we would interpret the second figure, our model 3, this is telling us the relationship after we've controlled for year built. So we're saying, what's the difference on average in price between two houses built in the same year, one that's slightly larger. And that's our beta 1 estimate. Okay, any questions here? So without control, we're saying the size effect could be inflated by the age effect, and that's sort of what we're seeing here. With the control, we get the size effect between two equally aged houses. And then this is doing due diligence. This is the residual plots. You'll notice a couple of things. First off, I don't love these residual plots. This is telling there's much more variability in the small houses. So the horizontal axis, I have the fitted values, and the vertical axis, I have the residuals. But by construction, they'll be centered on 0 horizontally. But you'll notice that there's much more variation in the smaller fitted values. So my prediction, when the prediction is a small price, then I get a lot of variation in the data. And then the same is sort of true with the Model 3 when you have the control variable. I would say it's a little bit better in Model 3 than in Model 1, but we still see a lot of the same problems. Namely, say it with me, heteroscedasticity. Yeah, I heard all of you say it all at once. Okay, so that's fine. Heteroscedasticity is something we know how to deal with. I would just include robust standard errors to deal with this problem. The core problem is that we would the p-values we would estimate would be partially wrong. So our model would be incorrectly confident. All right, any questions here? So the last thing, we covered this a little bit last class, but because we're using log as the outcome variable, I just want to spend a second to talk about log interpretation of betas when the outcome variable is log. We talked about this last class, but when the coefficients are very small, the beta itself is approximately beta times 100 percent change. So in this context, our beta 1 in the controlled model was 0.00045. So we multiply that by 100, which gives us an interpretation that looks like this. Each additional square foot increases the price by roughly 0.045%. This is a really small number and hard to internalize. So one thing we can do is multiply everything by 100. So all I did in the second line is multiply the increase in square foot by 100. So we're looking at what happens with a 100 square foot increase. And then we also multiply the price increase by 100. So I'm just moving 2 decimal places. So every 100 additional square feet increases the house by 4.5%. And you'll notice this is in percentages for price. The reason we're doing this is because our outcome variable, our y variable, is log price. So it's very difficult to interpret the beta directly. Goes up by 1 log unit. That's very hard to interpret. So instead, we translate this into percentages, which is part of the reason we use the natural log because of this approximation. This is not mathematically identical, but it's very close. Okay, any questions here? So some of you will use log as an outcome variable. The other thing we can do is talk about the estimate on year. We also got an estimate for the impact of an additional year newer on the price of houses. And what we found is that every year increases the price by about 1.5%, or 10 years by 15%, which is pretty substantial. All right, any questions here? And I guess I didn't include this directly in the bullet points, but this is all comparing 2 houses of the same year and compared to houses with the same area, which is what the control variables are doing. Okay, so that's the basics. We're going to get our hands on this data set and play around with it for a second, and then I'm going to let you go hang out in the sunlight. I guess you all are here voluntarily, so that's where you could be right now. Just picture yourself outside on Shenley Plaza, yet you're inside, hearing me drone on about something you already understand. Okay. Self-deprecation didn't work in that case, so I'll self-deprecate again. All right, so this is without controls. We're just comparing, we're possibly comparing small houses to large houses, which isn't very well controlled, especially when we think newer houses are larger. And so our beta 1 captures both of those things. And then with the control variable, now we're comparing apples to apples in the variables that we're considering. The thing to remember, though, is we don't have all of the variables that are meaningful. Like, there are so many things that would impact the price of a house. Like, is it well kept? That's very important. And that's not something we have measured in our data set. So there are lots of things. Think about the Simpsons paradox. There are lots of things that could impact housing prices that make this analysis imperfect. So all we're doing is comparing using the observations we have. Okay, so this is just a bit of the summary. It helps us isolate the main predictor. We can think in terms of like holding constant. I showed you what happens to the coefficients when we add control variables, which pulls out the confoundingness of the variable that we're adding. And then we're going to talk about confounders and mediators next class. The last thing we do is we check the residuals. We do this every time we run a model. At least that's best practice. Every time you run a model, if it's something you're interested in, you need to check the residuals. Okay, you want to do an exercise? You're inside when it's nice outside, so why don't we get some credit for it? All right, so I'll take that as a yes. Good enough for today. So I have two things posted here. I have the notebook and I have the Pittsburgh property values if you're interested in the data set directly. So you can just download that there. But for our purposes today, we're just going to access the notebook. Oh, look at that. What should I have done first? It matters less for me than it does for you, but I do it to set a good example, as they say. Okay. So I'm going to run the imports, and then we're going to load the data. I have the loading of the data in the slides if you want it. The main thing here, besides just loading the data, I also have, we're going to use sale price to find the log price. So I'm going to copy this over. When I run this, we can take a look at the variables here. So there's a lot going on. One thing we could do is control for zip code. So maybe houses are being built in different areas. If all the development that's happening in Pittsburgh is happening in like Lawrenceville, those houses are smaller than average, but also more expensive than average. So that could skew our data. Sort of, we'd be in sort of a Simpsons paradox world. So one thing you could do is include property value, property zip code fixed effects. So essentially, like 1,000 different intercepts for the different neighborhoods, which is definitely something you can do. We have the sale date. So a lot of these properties were sold a long, long time ago, which would tell you something about their price. We have the sale price, we have the number of stories, we have the year built, total rooms, bedrooms, full bathrooms, half baths, lots of different variables here. Finished living area is one of them that we'll use. We also have log price. I constructed this one called Area 100, which is finished living area, but divided by 100. So it's in 100 square foot units, which sometimes that makes interpreting the coefficients a little easier. So that's available to you. So this is what the data looks like. You can also find some of these property values are very small. So data, if we do sale price, and then I look at min, so I find the smallest one. I have a house that's sold for $4. We could also do histogram, so we just look at the distribution of sale prices. This isn't incredibly informative, but we could do log price. And you can see the distribution of prices. I think it looks better in Seaborn. This is a massive data set. Whoops, hist plot. So this is the distribution of prices, and this is one of those classic distributions where we would want a log. So log price. And this looks much nicer. There's still lots of very small values, but this is pretty good. We can find the size of the data set, so the length of the data. So yeah, maybe not that big. 10,000 observations is fine. So yeah, this is one of the variables we're interested in. Another one was we wanted the distribution of years. So SNS dot, let's do count plot. And yeah, we can do finished living area. Whoops, that's not what we wanted. I should probably take a class on data visualization, don't you think? So here's finished living area. Again, sort of downward skewed. So maybe you would want a log of this too. But we're not going to do that today. And then the last one, let's do hist plot of year built. So year BLT. Making me hungry. So here's a distribution of the years. So, you know, Allegheny County and Pittsburgh, the city itself, were built, you saw like a flurry of building after World War II. There's a lot of building in the early 1900s, and not a whole lot going on before like 1870. Okay, lots of very interesting data here. The next thing we're going to do is just set up the models. So here I have two scatter plots. I've given you the code to do all of this, and I'm just going to plot them. These are the figures I had in the slides. So horizontal axis, I have finished living area. Vertical axis, I have log price. And then for this one, this is the same I had in the slides. Horizontal axis, I have year built, and vertical axis, I have log price. One of the things that maybe makes this look weird is that this distribution is somewhat skewed. So it may be better to take a log of finished living area. Extreme values are unlikely, and small values are much more likely. So you could play around with that if you wish. The next thing we're going to do is just set up these regressions directly. So I'm just going to write down model 1, which is predicting using living area. So this is smf.ols, and then I'm going to try to predict log price using living area. I'm going to use finished living area instead of area 100. And I'm also including the robust standard errors here. It looks like there's the strong heteroscedasticity. So including robust standard errors sort of allows us to account for that more appropriately. And then I'll just run this one line. I get the intercept term and I get the finished living area, which corresponds to the numbers we saw in the slides. If you want to put a print around this, you can do that. I'm also, I think for our purposes later, I'm going to call this model 1. And then I'll print out model 1 summary below. Okay, any questions here? So this is pretty nice. This just gives us our baseline estimate. But let's build model 2. Gemini is getting a lot better at these things. We'll call this model 2, which is smf.ols. We have log price. And as our outcome variable. We have year built as our predictor variable. And then we're including robust standard errors, covariance type HC3. And then the last thing we'll do is just print it out. And this gives us the estimate for the value of every additional year on price, which is approximately 16%. Any questions here? So the last thing we'll do before we run the full regression is to plot the relationship between the two variables. In the slides, I had this flipped. I had year built on the vertical axis and finished living area on the horizontal axis. I think this is a more natural way of plotting this. And it seems to, I mean, this definitely looks like there's a slight upward relationship in finished living area through time. So newer houses seem to be bigger. So this indicates that we should probably include this as a control variable, year built. So that's what we're doing here. This is model 3. You can find this in the slides if you like. You can do this here. And if we run it, we get the full model, which gives us, so this is area 100. What if we normalize this to be in terms of 51 square feet? We'd call it. Who comes up with these jokes? It's a real pleasure that you laugh at them. So all I'm going to do is just use finished living area. We could change everything to be in terms of 51 units, 100 units. But I'm just going to go back to our original units. It makes it a little bit harder to interpret this, but this is fine for our purposes. And then the last thing I'll do is plot the different models. Maybe the slides. So you're going to have to change some of this code to correspond with the different models. Without control, we called this model 1. So I'm just going to call this model 1. And then the control variable was the controlled model was model 3. So you can just change those things. Oh, I guess we call this model both. We call this model 3. And this is going to give us the residuals from both of our models. And like I had in the slides, this was, I think, this is pretty good. As long as we're handling robust standard errors, handling heteroscedasticity with robust standard errors. Okay, any questions here? So Gradescope will ask you to interpret the betas. So I think a lot of the interpretation for the exercise is in the slides. But the way I would say this is that finished living area goes up by roughly 0.5% for every additional square foot. If you wanted to convert this into 100 square foot units, you could do that just as well. And then the beta 2 here, so this is roughly 1.5% for every year. So the value of a house goes up on average roughly 1.5% for every year newer it is. So 1 year newer, it's roughly 1.5% more valuable after controlling for the size of the house. So I'm not sure I said that in a complete sentence, but that's what I would write. Okay, any questions here? Good as gold. So that's almost all there is to it. We talked through the interpretation of these of control variables. The idea is very similar to what we've done in part 5 so far. We have control variables which allow us to isolate the other variables that we may think are related to our outcome variable. And what this does is allow us to avoid some of the issues of Simpson's paradox. Of course, we'll never completely remove the problem of Simpson's paradox, but this allows us to at least control for some of the issues. We talked about interpreting logs. I think this often can sort of trip people up. Okay, so I think we'll maybe leave it here. If you have more questions about the exercise, we can stick around. If you have more questions about your final projects, now's a good time to work on that. You could also take your group outside to Shenley Plaza and hang out there and work on your projects, which is actually what I would recommend. But if you have questions for me, feel free to stick around.